Okay. Do you hear me?
Yeah, we can hear you.
Okay. Thank you. Welcome again. I am the moderator of this symposium, Dr. Mehmet Fethi Ertenli. Welcome to third International Symposium of Engineering Applications on Civil Engineering and Earth Science 2021. First of all, the editor of this symposium, Dr. Inan Keskin, will greet you. Here you are, Dr. Keskin.
Thank you very much, Dr. Fethi. Welcome all participants. Dear participants, welcome to 30th International Symposium of Civil Engineering Application on Civil Engineering and Earth Science 2021. Before starting my speech, I would like to thank a special Dr. Jo, Dr. Erdik, Dr. Shahmaran for their contribution to symposium as keynote speaker. And also I would like to thank organization committee and all participants. The data obtained from scientific studies are developed with academic participants, and because this pride does contribute to science. This symposium has been organized with the intention of servicing this purpose, sharing and spreading scientific knowledge. International Symposium of Application on Civil Engineering and Earth Science aims to global platform civil engineering and earth science. This symposium covers all major aspects of earth science and civil engineering with related topics. This symposium includes 26 papers and their great keynote from different countries. I hope that symposium outcomes of the paper will serve as a valuable reference to all surgeons, students, and as well as engineers from all sections of civil engineering and earth science. Due to COVID pandemic, this symposium unfortunately has been organized only online this year. But we look forward to you in Karabük University next year. I respectfully greet and welcome all you. I hope see you again at our next symposium. This symposium language is English and Turkish. I would like to some speak at Turkish language. Şu an online olan tüm katılımcı arkadaşlarımı sevgi saygımla selamlamak istiyorum. Sempozyumumuzun dili hem Türkçe hem de İngilizce. Uluslararası bir sempozyum var. Dünyada iletişim için kullandığımız yegane dilin İngilizce olması hasebiyle ve uluslararası niteliği ön plana çıkartmak amacıyla sempozyumu birincil dil olarak İngilizce yapıyoruz. Ancak sempozyumda şu an sunum yapacak arkadaşlarımızın tercihleri bazen Türkçe dilinde de olabiliyor. Proceeding book'umuzda da Türkçe bildirilerimiz var. Şu an katılımcı arkadaşlarımızdan bildirilerini Türkçe yapmak isteyen arkadaşlarımız olursa bunda herhangi bir problem yok. Öncelikle onu ifade etmek istiyorum. Tamamen kendilerinin tercihlerine bırakılmış bir durum. Türkçe ya da İngilizceyi diledikleri gibi kullanarak anlatım yapabilirler. Yer İngilizce, yer Türkçe'de kullanabilirler. Bununla ilgili bir problem yok. Biraz önce ifade ettim arkadaşlar. Sempozyumdaki genel kaide sadece bir bilimsel etkinlik yapıp orada kalsın değil. Biz bu sempozyumu rutin her yıl düzenleyerek alanında inşaat mühendisliği ve yer bilimlerinin bilimsel gelişmelerini büyük kitlere ulaştıracak global bir oluşum haline getirmek istiyoruz. Bunun için tüm katılımcıların destekleri bizim için vazgeçilmez derecede önemli. Sadece bu yıl için değil, gelecek yıllarda, sonraki yıllarda da hem katılımcı olarak hem de arkadaşlar bizleri yönlendirecek şekilde desteklerinize, güçlerinize ihtiyacımız var. Lütfen bu desteğinizi, ilginizi
Hocam seste bir kesilme oldu. Tekrar açmanızı rica edeceğim.
Özür dilerim. Ben konuştum ama ses kesilmiş bağlantıdan dolayı. Özür diliyorum. Gelecek yıllarda yine birlikte olmak umuduyla hepinizi tekrar saygıyla selamlıyorum arkadaşlar. Umarım sempozyum amaçladığımız hedeflere sizlerin sayesinde ulaşacaktır. Teşekkür ederim Dr. Peter. Thank you very much Dr. Peter.
Thank you, Mr. Keskin. Let me start the symposium with the introduction of three valuable keynote speakers. Dear Dr. Zhou, Dr. Shahmaran, and Dr. Erdik will deliver their speech respectively. Before inviting Dr. Zhou, I would like to share his great curriculum vitae with all participants. He is now participating in the symposium from the USA. Shusong Zhou joined the School of Sustainable Engineering and the Built Environment at Arizona State University in 2013. Previously, he was an associate professor at University of Utah. Zhou's research work focused on dynamic traffic assignment, traffic estimation and prediction, large-scale routing, and rail scheduling. He has been assisting the Federal Highway Administration to develop and provide technical support for large-scale simulation-based dynamic traffic assignment systems for the past 10 years. He served as an associate editor at the Transportation Research Part C, Emerging Technologies. He has published more than 30 papers related to dynamic traffic assignment and rail operation research in transportation. Zhou is the co-chair of the IEEE ITS Society Technical Committee on Traffic and Travel Management, co-vice chair for Institute for Operations Research and Management Science, Railway Application Sections. He also serves as the chair for the Network Equilibrium Modeling Subcommittee in TRB Committee on Transportation Network Modeling. He is also the co-inventor of Key to Safe Driving Technologies, which has been reported by more than 300 media outlets, including New York Times, Wall Street Journal, and National Public Radio. Students advised by Zhou have won a number of awards. Jeffrey Taylor received the Council of University Transportation Centers Pekarsky Awards, Science and Technology. 2014. Tai Shi won the first prize in Management Science in Railroad Applications paper contest, Institute for Operation Research and Management Science, 2014. Tao Xin, Kenneth Williams, Rohan Mata, Daniel Van Tassel won Windows Mobile Awards, Microsoft Imagine Cup Student Technology Competition 2009 out of 125 participating student teams in the US. Now, I kindly invite Dr. Zhou to deliver his speech. Dr. Zhou, can you hear me? There's a connection problem, maybe. One minute.
Begin. My name is Su-Song Zhou. Today is my great honor to present our recent research in this great conference of International Symposium of Engineering Applications on Civil Engineering and Earth Science. Currently, I'm a researcher at Arizona State University, United States. Today, my topic will be smart community rising up with a digital twin, and I will focus on how we can transform the interconnection between open data, researchers, and the city planners. As we all know, the evolution of the digital twins recently creates a lot of new research areas for us. Coming back to 1960, we have the computer-driven simulation. Then 1985, we have AutoCAD become an industry tool for us to integrate the different computer-driven simulation. And starting from 2011, NASA white paper defines the prototype of the digital twin. And recently, there's a lot of smart city applications try to list the digital twin and the smart city as a fully integrated research direction and the great application in the next 20 years. In my talk, I will focus on from the perspective of civil engineering researcher and the application domain in transportation. Let's look at the background on digital twin in the case of transportation planning. Look at how we use the open specification to bring our community together. And then I will use the virtual track-based system design as a prototype of the digital twin. And this is followed by the detailed simulation framework, plus how we define the smart system in the civil engineering to bridge the gap in our modeling area. I have the following research questions to be addressed in my presentation. When we talk about the smart community or smart city digital twin, SCDT, can we practically build a prototype for those smart city and the community very quickly? How we can encourage interesting and effective collaboration from our different partners, industry partners, researchers in the university, planners and engineers in different fields. Second question, can we utilize the open source tools, open data standard to enable this decision intelligence? Number three, when we try to build a high fidelity simulator to replicate the physical world of our transportation system in particular, how we are going to build it and what are the design principles. Last, but also most important for us to ask, can we use analytical forms, theoretical research to bridge the gap into these digital twin and the physical world representation? in particular, let's look at the different layers of representation. So our research line along this direction start with the open data standard, and then we are looking at the different layers of the network in the connected automated vehicle simulation and optimization. And then we try to build the internally consistent multi-resolution model to replicate the digital twin as an example of the physical worlds. In the last 10 years, my research team at ASU has been assisting Federal Highway and the US DOT and the different NPOs to provide dynamic traffic assignment, dynamic traffic simulation in different cities and states in the United States here. And as you can see, Phoenix is right next to California, and we are one of the rising cities to provide this smart city application, and we have host many companies such as Intel, and ASU is one of the largest city and one of the largest universities in the United States in terms of the number of undergrad students and in terms of the patents. So what are the critical challenges we see in transportation planning? I think on the right, you can see we have different components of our transportation planning. One of the key challenges in building the smart city or smart community digital twin is how to integrate the data at the different scales, at the different resolutions. When we try to integrate field sensor data to transportation planning model into the micro simulation model, when we try to provide the signal timing into different components, we can classify them into two types of connection. One is direct connection. For example, we can have the traffic count data fed into our demand model. One is some kind of cross-resolution coupling. If you try to use second-by-second signal timing data in large-scale simulation, there's a different layers for us to bridge the gap. And we cannot simply just take a second-by-second simulation results into an extremely large, complex city-scale simulation. So how to enable the consistency between different objectives, decision makings, and execution, presenting critical challenges for us. Since I working with the US DOT for a very long time period, I would like to introduce in the United States from Federal Highway perspective or from the different NPO, city, industry, academia partners. We are interested in providing GAMS, General Model Network Specification, to different transportation representation from the link level, lane level, and then from the different detailed pedestrian bicycle lane representation. So we can enable this multi-modal digital twin physical model. And on the bottom of this slide, I try to show that actually we have some success stories for GTFS, which is General Transit.
Dr. Zhu?
Yes, I'm here. I think,
Okay.
as we can see, the digital twin always has a reliability issue. So, this is my physical person.
Oh, yes, I understand. Will you continue to presentation?
I think I can just do the live presentation if you prefer, or I can also just play the video and wait for the question at the end.
Yes, it's up to you, Dr. Zhu. You can go on, please.
Okay. So I think let me just do the online presentation so we can see a copy of the digital twin in real life. Okay, thank you. So let me just go ahead to present my slides and make it more interactive.
Welcome again.
Okay, can you see my full screen now?
Yes.
And I will move to the slides.
We can see.
Yeah, I will move to the slides we have right there, and we should able to cover the material right here. Okay. So as we can see, as we assist in the find a highway to build the digital twin data hub, we are connecting different dots, including big data, demand side management, traffic simulation, operations, and the control model, all into the digital hub of SCDT. So I will go a little bit fast to talk about all different open source tools, including my student Jay. We have been producing this OpenStreetMap to the GMS Data Hub tool, really for the purpose of building a digital twin. On the left, you can see we have building this whole United States highway network, and with about 10 million nodes. If we try to digitize further lane by lane, you can see the magnitude of the model. And we are using a supercomputer with 4 terabytes of the memory to process this data set. On the right, you can see, and one interesting to see, there's also Turkey version of the OpenStreetMap. I'm happy to work with your students, your great faculty members to apply this OpenStreet to GMS2, and currently our tool has been installed more than 20,000 times. So after you build the network, you can also create the cell-based or the grid-based chip generation to generate the different type of the modes, including travel, biking, bus, and for these connected automated vehicles. We have other faculty members such as Milan from University of Miami, and he's creating a link to create the importing utility from synchro, from the commercial signal timing, second by second into the data hub. We have our former graduate from ASU, Professor, I will say Dr. Pei-Heng Lee, currently working at largest railway company, Norfolk Southern. He created the path for GMS using this specification, providing this accessibility calculation, shortest path calculation, and for the very large scale network. We also have Dustin, who is one of the open source developer for AB Street, mainly for the community service. And using the same data specification, he can generate realistic traffic demand, and he can also produce this second by second simulation according to our signal timing. So in the long run, we try to build these different categories, A, B, C, and D. A, including the network. Basically, we try to get OpenStreetMap to the model network, generate the OD demand, generate the traffic demand. Then from the B, we can get the traffic capacity. From the C, we can run the different types of models. Finally, we will reach the goal of consistency representation across different domains. So now let's go to the second level of our smart community digital twin. After we have this open data specification and open tool, now we are able to build a high fidelity, fully integrated CAV. CAV stands for Connected Automated Vehicle. And we can try to extend from a macroscopic regional level to the micro lane by lane, side by side representation. So I think if you have the transportation faculties or computer science faculties in this domain, you might know Sumo, coming from Germany, is one of the leading space continuous time discrete traffic simulator. So essentially, they have built a good community along this line. But we do see some challenges, such as high complexity when we try to handle this very large scale network, and how to enable distributed control and try to provide the safety guarantee in real life application. So along this line, I think we do see the challenges of implementing an integrated simulation, optimization, and a control framework. So that is why when we say digital twin is not simply just a simulation, it's a platform for us to enable the high level optimization and online control. So by doing so, we will be focusing on new modeling framework to enable these simulation, optimization, and control methodology. So I think I was before the conference, and I'm very interested to see you have this wonderful state-of-the-art high-speed rail in Turkey. As you know that I'm just using some statistics from China. The accident rate of a high-speed rail or the regular rail will be much lower than the typical highway network. What's the secret weapon we have from the high-speed rail? They have different types of the blocks. A block is defined in the railway system as this mechanism. Only one train, or at the most one train, is allowed to occupy a certain segment of a given time. So thanks to the technology advancement, we see from the development of the manual block 100 years ago, moving to the automated block, thanks to the 6G, 5G network. Now we have capability of consider the moving block to keep the safe distance from leading trains. So in this way, we use this virtual track terminology to digitize the physical network to this meter by meter cyber track network. So as you can see clearly on the right, we have car following tracks, we have lane changing tracks, and we can design this emergency response track. Try to consider all these detailed representation and building these realistic digital twins to the physical system. So I want to show you one of our work in progress. We are building an open source package, which is called CAV Light. CA, again, stands for Connected Automated Vehicle. And the CA also stands for the Cellular Automata Model. So by using this representation, we are able to integrate the simulation optimization in a discretized network. So let's zoom into this one of the interchange. Here is meter by meter. In this scale, I use the 7 meter by 7 meter digitization and to show all the potential lane changing and all the merging positions. And by using this kind of network representation, we are able to model the lane changing, model this link choice, model all these car following in a space discretized environment. So in this case, if you look at how the vehicles are moving from an intermediate origin to an intermediate downstream destination, this can be used as optimization problem very precisely with the different types of the cost, such as expected cost to the final destination, waiting cost to the intermediate destination, and the moving cost to the next action. By doing so, we will be able to create the virtual connection from the cell and from the microscopic link to the traffic signal control. So you can see on the in the middle of the graph, we have this red representing is a certain cell has been blocked, and the green represents this certain cell are able to provide this access for the different vehicles. So I want to just demonstrate how we can use a streamlined process for this CAV Light as a prototype of this automated vehicle digital twin. Prepare the network, prepare the OD demand, calibrate the corresponding routes, perform the simulation, visualization, and the final output. So one of the very nice features here is we build the mapping consistently between different layers. On the very left, so you can see this is intersection expanded to the different movements and then further extended to the left turn, right turn, different changing lane cells. And all those network representation are based on the Fiber Highway GNMS open standard. So because the open standard was out just last year with the version 1.0, so I think in the long run, in the next 2 or 3 years, many companies, many researchers will have opportunity working with us to provide this kind of open data platform. So by using this, we are also interested in the mixed traffic control. We need to guarantee the safety using the moving block concept, and also we can provide this cell-based network mapping to consider what are the best merging points on the freeway and what are the best lane changing points in a discretized world between CAV as a connected vehicle, HDV as a human-driven vehicles. By using this digital twin representation, we are able to address the question such as how to calibrate the behavior model, how we can continuously map the position into time digitalized version. Here is one of the mathematical details we may need to consider. We always try to make the two-dimensional representation. So you can see the time axis are the second by second. In our optimization, we use a 0.1 second resolution. Space, what if similar to the high-speed rail? Most of the trains are moving forward. If you have multiple lanes, we need to map this two-dimensional space into a one-dimensional domain. So in this way, by using this waiting arc, they wait at the same position in red, or traveling arc, we are able to literally control the space and the time and the speed trajectory of the automated vehicles. I don't want to go into any further details. This is just one of the typical example of building integer programming formulation for this vehicle control. And this, all those papers are typically published in one of our leading journals, Transportation Research Part B. And luckily, I'm one of the top 5 authors in the last 10 years in terms of the publications for this journal. So the key is all about trying to build the open source, open standard platform and have enriched mathematical modeling along this line. There are still a lot of challenges. If we simply model this problem as an integer programming problem, we have a large number of integer variables to consider. So the solving time could be extremely long, and then this raises some further research questions and challenges for us. So then I will go to the third layer or the third level of the digital twin. Again, first layer is open data. Second layer is the high fidelity network representation and simulation and optimization. The third layer we can reach will be the smart, consistent management of the system. So I highlight this keyword of internal consistent mapping for the large scale system. In our traffic flow theory, we can have these analytical results between the car following model and the aggregated speed density relationship. And this is one of the leading theory in our area. Fortunately, my former professor, Professor Haniman Masani, who is also a National Academy of Science or National Academy of Engineering member, and he was getting enough advice from the car following model from Dr. Herman. So now, if we look at the historical perspective, back to 1930s, 1960s, there's a number of the car following models and the traffic flow models developed. They are not so perfect in terms of if you only have 2 or 3 variables, it's very difficult to fit the human behavior. If you have too many variables, and then you can feed the elephant with many different interpretations. So we're looking at this challenge. We recently just published a paper which is called S3 as S-shaped 3-parameter models. So here we have 3 parameters: free flow speed, VF, critical density, KC, the aim as the maximum flow inertial coefficient. I believe that in the different countries, we can just use an example. In Germany, you have a very regulated high efficiency performance. So the aim factor can really maximize to 8. And in the United States, based on our observation, we are around the range of 4 or 3.5. And in other countries, if you have a mixed traffic, you might in the degree of 2 or 2.5. So by using these parsimonious models, we are able to characterize the system, provide the consistent results, and try to provide opportunity for researchers to think how we can maximize the flow throughput and using this M factor. So I don't want to really go all the detailed derivation, but it's really just an exercise of advanced calculus, and we are able to calculate this and present this wonderful three-dimensional representation, because everything here is a three-dimensional curve, and when you try to look at the mapping from the density, speed, or flow, speed, or density, flow, all these three dimensions can be viewed as a projection from a 3D system. Okay. We further develop the theoretical Carfolian model. We are hoping this is one of the new analytical results for researchers to think how to do the trajectory control and leading to the capacity maximization. So this is our sample data set from US 101. And I'm very glad to report that through our newly established model, if you look at all the literature here, this is S3, and in terms of the relative measures of error, okay, we are #1 in the limited test in terms of the average MOE, average relative percentage error, and the standard deviation. I want to also say the smart management in the smart community digital twin requires us to think from the systems perspective. So along this line, I have opportunity working with many talented researchers, engineers to look at the problem, not just on Carfolian, but also looking at on the traffic congestion bottleneck along the time domain, how we quantify the congestion peak period in 7 to 8, or if a traffic jam is extended for 3 hours, how we define the congestion period, how we can use the different analytical model to quantify this impact. So very luckily, I have our friend, Dr. Baloka Balazema, and currently he's also the senior transportation planner at the Arizona Department of Transportation, and very fortunate I have opportunity working with him to present the smart management analytical formula. The x-axis try to show you this is the demand over capacity ratio. Y-axis will be the speed, speed in terms of miles per hour, and we categorize the system into different regimes. Region A as uncongesting curve, region B as over-congesting, but somehow it's very difficult to understand the congestion demand for a longer period of time. So we further derive the mapping into region C, try to provide a more system perspective for this management. So last stage, after these 3 levels of digital twin development, we are happy to provide some informed decision support for digital twin. At this stage, I'm very busy for developing the prototype for 2 very large regions, one in Arizona, the other is in Washington, DC and the surrounding areas. We hope by using our digital twin representation, we can help the agency to design the better planning model and better perform their programming tasks to allocate the different funding to different much needed projects. Last slide. This is a great opportunity for me to present our recent results on new perspective. On the top, I try to show this is our ASU Transportation plus AI Lab. We are hoping we can try to use the different tools to build the connection between physical system model and our digital twin representation. On the bottom, very importantly, we hope this dialogue will enable us to really work together, try to digitize all these different land use, highway network, high-speed rail network, water, river networks, and then by doing this together, we hope we can perform, optimize the system into the future. Again, thank you for your opportunity, and I'm glad to take a few more questions.
Thank you, Mr. Zhou. Thank you for presentation. If you want any questions for Mr. Zhou, dear participants, please click the raise hand button for ask a question.
Okay, if not, I'm glad to have this opportunity. I think will be really the. I also see, we have a former ASU friend, Kaffer here. We hope we can try to build not just only the Turkey network and the whole EO network together, and all those advancements will help your faculty member, your talented students who really show the great asset of the students, and then to advance our collaboration together. So thank you for the opportunity.
Thank you so much, Mr. Zhou, for attendance and presentations. Dear participants, we thank him for very valuable speech. Thank you for listening. Now, the next keynote speaker, Dr. Shahmaran, will share his scientific knowledge with us. Welcome, Dr. Shahmaran. Can you hear me?
Good morning, everybody. Can you hear me?
Yes, sure.
Okay. So can I share my presentation?
Sorry, before starting your speech, I would like to introduce you briefly. Mustafa Shahmaran received his PhD in 2006 before completing his postdoctoral fellowship at Michigan University, US, and Ryerson University in Canada. He is currently a full professor with the Department of Civil Engineering at Hacettepe University. His current research interests are in micromechanical design and durability of high performance and ultra-ductile cementitious composites, recycling industrial and natural waste products into useful construction materials, and nano-modification in cementitious systems. Dr. Shahmaran is a member of several technical committees of the American Concrete Institute, American Society of Civil Engineering, US Transportation Research Board, Turkish Society of Civil Engineering, and the International Union of Laboratories and Experts in Construction Materials, Systems, and Structures. Dear Shahmaran published over 100 peer-reviewed research articles in major scientific journals and conferences. Professor Shahmaran received the Province of Ontario Fellowship in 2007, a Sertümen Research Award in 2012, Turkish Academy of Science Distinguished Young Scientist Award in 2012, Professor Dr. Mustafa Parlar Education and Research Foundation Young Scientist Research Incentive Award in 2013, Dobitak Young Scientist Awards in 2014, Favored Sertümen Distinguished Achievement Award in 2015, Society of Science Heroes Young Scientist Award in 2015, Hacettepe University Science Incentive Award in the field of science and engineering in 2017, Turkish Academy of Science Young Scientist Award in 2018, and American Concrete Institute Weighton Medal for Material Research in 2018. Now, I kindly invite Dr. Shahmaran to deliver his speech.
Okay, thank you very much, Mehmet. So can you see my presentation?
Yes,
Okay.
I see.
So good morning, everyone. My name is Mustafa Shahmaran. Today, I'm talking about the integration of sustainability aspects of additive manufacturing method into new generation green construction materials. Before going to details of my presentation, I would like to talk about the outline of this presentation. And in the first stage, I will discuss the relationship between the construction and sustainability, specifically concentrating on the concrete materials. I will then make a presentation on the construction demolition waste. Shortly we say CDW and CDW-based geopolymer binder. And I will conclude my presentation with the topic of 3D concrete printing technology and its use for CDW-based geopolymer binders. And if we are going to have a time, I will shortly mention about the future research needs. So as you can see from this figure, structures are seeming to be in all places in our life, and high amount of concrete is cast for construction of the structures. For example, buildings, infrastructures, bridges, highways, airports, among the worldwide. And by many measures, concrete is still an excellent construction materials. While it's widely recognized that civil structure supports the health and the wealth of the nations, it is disturbing that the general condition of the infrastructure in many nations, including our country, are deteriorating rapidly. So why do we use the concrete with this amount? Because the concrete is a material which is easy to make by mixing its ingredient easily. For example, water, cement, sand, gravel, and other needed admixtures, including chemical and the mineral admixtures. Plus, concrete is a material which is easy to cast because of its flowable, sprayable, moldable character. And nowadays, we are also dealing with the properties of the printability of the concrete. It can be printable if we are going to make an appropriate modifications in its fresh properties. Concrete is a safe material, construction material, which is a fireproof and relatively resistant to seismic loads if we are going to design properly. And its properties are known and historically proven, and its utility is very common. These are the general advantages of the concrete. However, the mechanical and the functional characteristic of the concrete will have to be improved in some ways significantly. And these improvements are already emerging in limited forms. These advancements are needed to address deficiencies in concrete structures. Currently, if we are dealing with the problems in reinforced concrete structures, we have three challenges that needs to be overcome. One of them is lack of safety under extreme loading because of the brittle nature of the concrete. The second one is the lack of durability for the long-term use. And the final one is the poor sustainability. This is one of the main topics of today's presentation. I mean, it is environmental impacts of the concrete infrastructure. And the infrastructure challenges suggest that the future concrete must have the following characteristics listed in this presentation to make the concrete more sustainable. First of all, it needs to be high ductile with the ability to yield like a metal when it is overloaded. And even under severe impact load or large imposed deformation, therefore, it's going to provide infrastructure safety. it has to be highly durable with the ability to withstand, to resist mechanical and the environmental loads under normal service conditions, therefore providing service life significantly higher than the current infrastructures. As you know, nowadays we are expecting more than 50 years for the service life of the important infrastructures, including bridges, airports, dams. And the concrete materials should be highly sustainable. How we can deal with this problem if we are going to minimize the natural resources used and the pollution emission during the full life cycle of an infrastructure, therefore ensuring harmonious interaction between the built and the natural environment, mutual interaction. Also, novel viable construction techniques, as in the additive manufacturing or 3D printability, should also be developed. So let's just consider the ingredient of one of the main ingredient of the concrete, cement. It's one of the most important ingredient. So when we consider the cement as the main binder of the concrete globally, there is an increasing trend in the cement consumption. And as the emerging countries such as Turkey, when we continue to develop, the trend is expected to continue increasingly. However, the common usage of the concrete has many detrimental effects in terms of the sustainability. For example, it has a very high energy consumption, and as a second detrimental effect, it has a very high CO2 emission. Let me mention about the let me give you some information about the CO2 emission. As you know, the production of 1 ton of Portland cement requires around 1.5 tons of raw materials. What are these? Limestone and the clay. And it's going to release around 1 ton of CO2 to the atmosphere. For example, according to the European Cement Association report in 2014, cement industry alone contributes around more than 6% of the global environmental pollution by CO2 emission. Plus, as a final detrimental effect, the first one is high energy consumption or demand. The second one is high CO2 emission. And the third one is a final detrimental effect, depletion of the natural resources. As I mentioned before, to produce a ton of the clinker, more than 1.5 tons of the rock or clay is needed. These are the huge numbers that needs to be overcome quickly, otherwise some serious problems, including climate change, will happen, including our country and all around the world. And due to the ever increasing the urban population and the continuously developing economies of the countries in the world, construction and the demolition application have become one of the leading sectors in the world, with the increased number of the repetitive repair, renovation, maintenance of the buildings, roads, bridges, and other structures. Each year, significant amount of the solid waste are generated as a result of these applications, requiring to be tackled properly. And for example, if we consider the Turkey example, more than 6.5 million structures are expected to demolish under the action of the infrastructure and urban transformation. Considering that the whole building stock in this country, it's around 19 to 20 million, it is an important issue of the concern what to do with the expected construction and demolition waste generation. And in the right, we can see the share of the different economic activities and households in total waste generation in 2016 in this figure. And only in the European Union, construction contributed more than 36% of the total waste. This is a huge. And the main sources of the waste generated, when we consider the all waste generated in European Union. Therefore, construction and demolition waste industry is the largest, not one of the largest, it is the largest global solid waste producers, accounting for 30 to 40% of total urban waste. And only in Europe, every year, more than 180 million tons of the construction demolition waste is produced. The situation is worse in our country because of the urban transformation laws. These are some pictures obtained from the forest area. And if we consider globally, there are multiple adverse effects of the construction demolition waste. For example, waste landfilling of very large clean lands and the forest or the lakes or sea, and causing hazardous pollution which jeopardize the surroundings, and plus it wastes our natural sources. So for that reason, in most of our research, we concentrated on these topics. Although zero construction demolition waste seems unpractical since the waste generation is unavoidable, effective solutions to minimize the amount of the construction demolition waste generated must be sought for the sake of the environment, social, and the economical benefits. In our research, we have set the goal of the developing construction methods in such way that over the entire life cycle, they present better environmental properties than the respective predecessor materials. Considering the fact that construction demolition waste can be easily obtained anywhere in the world or any city in our country, utilization of the CDW-based source material for example, geopolymerization or for the conventional methods is an other alternative method for manufacturing of different construction materials. Usage of the CDW along with the industrial byproducts, for example, slag or fly ash or silicopium as an aluminosilicate or alkaline actuator source is expected to make a significant impact on the preservation of the natural resources, environmental considerations, people's health, and cost of the initial materials. Therefore, we have been working on a new generation of the geopolymeric binding material for a long time, and we have come a long way in this direction. And we are now studying on this binding material to improve its rheological and its insulation property to obtain all of ergonomic, economical, and environmental benefits. And we try to modify the properties of these materials which is suitable for different kind of the structural or the construction application, including 3D additive manufacturing. So in this slides, for this study, we have obtained construction and demolition waste selectively from different parts of the Turkey as a concrete waste or brick waste or glass waste. The first important rule is we need to select the materials selectively. Actually, this is not very difficult, and this process is generally applied in most of the developed countries. And if we are going to collect the samples, construction demolition waste samples selectively, first of all, the materials were each milled in a jaw crusher at a size less than 1 millimeter and milled at the time in the ball mill until reaching the fineness of the cement. Particularly for concrete waste, we did several different kinds of the application, and what we obtained, it is more appropriate to graph the size of the concrete directly obtained. We do not need any additional procedures to obtain the concrete waste as a powder or as an aggregate particles. And you can see the chemical composition of the construction demolition waste in this table, which are obtained from different parts of the Turkey: Istanbul, Izmir, Konya, Ankara, Sivas, Trabzon, Batman, Gaziantep. And at the end of the table, you can see the chemical composition of the fly ash, which is commonly used in the production of the concrete. When we examine in terms of the different oxide content, the chemical composition of the construction and demolition waste are very similar to the fly ash or very similar to the pozzolanic materials. Therefore, why we don't use these materials in the production of the geopolymer or conventional concrete commonly? Okay, we know there are some experimental or scientific studies on this topic, but as far as in our knowledge, there are not so many studies in our country about the practical use of this material for the real construction application. So firstly, we studied what is our purpose. Our purpose is to develop a new material with 100% construction demolition waste, only including CDW. So firstly, I think 2 years ago, we started to develop different kind of the binder from our materials. And we studied on the paste specimen without aggregate, and we obtained our best results as around 60 megapascal. In here, you can see 59.8 megapascal under 72 hours at 90 centigrade degree thermal curing process. That's good, but there is a thermal curing process we do not prefer, and it's not possible to use this thermal curing process in real field application. After that, we produced the mortar specimens. We added fine recycled aggregate to the paste material, and by incorporating waste aggregates to the paste mixtures developed in the first stage for further recyclability. And different kind of the alkaline activators tried in different combinations and at different rates. We obtained our best results as around 50 megapascal under 72 hours at 90 centigrade degree thermal curing process by using ternary use of the sodium hydroxide, calcium hydroxide, and sodium silicate as an alkaline activators. We also developed concrete mixtures. These are the concrete mixtures with 100% construction demolition waste, both paste binder phases and the aggregate phases directly obtained construction demolition waste. And in these mixtures, we were able to obtain a strength higher than 30 megapascal under ambient curing. That's great. Under high thermal temperature, around 90 centigrade degree, in 3 days, the concrete strength is going to be more than 47 megapascal. But in ambient curing at room temperature, we can easily obtain 30 megapascal, which is similar to the typical properties of the normal strength Portland cement concrete mixtures. So we also included fiber materials to the construction demolition waste-based geopolymer concretes to obtain high ductility or bendability of green CDW-based engineered geopolymer composites, shortly EGC. And in this way, we obtained engineered cementitious composites which have high resistance to the large cracks, resulting multiple narrow spaced crack formation, as you can see the figures or photos in the middle of the presentation. We obtained our best results among 100% construction demolition waste-based engineered cementitious composite as more than 45 megapascal after 72 hours thermal curing. After that, to further improve the properties of the engineering geopolymeric composites, new mixtures were developed by replacing 20% of the precursor material by slag. So there is a construction demolition waste, plus we have added a small amount of the industrial waste. It is slag, blast furnace slag, around 20%. This replacement provided visible improvements in the properties of the mixtures. CDW is west, slag is west. We combine these two west and we obtain synergistic performances. And figure shows a typical, the figure on the left, upper left side, it shows the typical flexural stress deformation curves of the EGC containing around 1.5% polymeric fiber. And the characteristic of the flexural hardening after the first cracking is accompanied by multiple micro cracking. And the crack width development during the inelastic straining is also shown in the middle of the presentation. There is a photo that shows the crack characteristic of the specimens. As you can see here, even at ultimate load, the crack width remains 100 micron. This tight crack width is self-controlled, remains less than 100 micron, and whether the composite is used in combination with conventional reinforcement or not, it is a material characteristic independent of the rebar reinforcement ratio. But in the case of the conventional reinforced concrete, it relies on the steel reinforcement for crack width control. This will provide us a significantly higher durability performance because of the high ductility and crack healing or sealing properties during the exposing to the atmosphere. So this figure shows the effect of the substitution of the 100% clinker by 100% of the CDW-based new generation geopolymeric binder. Under this condition, the production of 1 ton of Portland cement is associated with a total CO2 emission of more than 850 kilogram carbon dioxide per ton of the cement. As a result of the clinker substitution with 100% CDW-based binder, a reduction in the specific fuel-derived CO2 emission is approximately 266 kilogram per ton of the cement. Additionally, energy is necessary for the selective demolition of the construction demolition waste. This is around 18 kilogram carbon dioxide per ton of the cement. And by far, the greatest saving effect is produced by the reduction of the raw material related CO2 emission from the limestone. As you know, limestone is one of the main raw material of the Portland cement. It causes significant amount of the CO2 emission, around 430 kilogram CO2 per ton of the cement. Therefore, if we are going to replace the Portland cement clinker with 100% construction and demolition waste-based material, reduction of approximately more than 700 kilogram carbon dioxide per ton of the cement is obtained. This means that 90% reduction. This is a huge amount of the reduction in CO2 emission. After complete recycling of the currently unutilized portion of the construction and demolition waste for green geopolymer concrete production, to adapt 3D concrete printing to the developed green geopolymeric concrete made from the waste material, which is indispensable option for sustainability development. So we need to develop a special manufacturing to make our methods more sustainable. The implementation of 3D additive manufacturing with construction and demolition waste-based geopolymer concrete contributes to ensure environmental friendly, economic and sustainable construction process as well. Therefore, the production of CDW-based geopolymer concretes that have proper features required for 3D additive manufacturing has a great importance. And after this point, we have started to modify the properties of CDW-based green geopolymer concrete for the purpose of the 3D additive manufacturing. In conventional formwork system with traditional concrete, one, we need formwork, which is responsible about 80% of the total cost of the concrete construction in most of the time. Two, the significant amount of the wastage generated in the construction, and another challenge. Formwork is a significant source of the waste since all of it is discarded sooner or later, contributing to a general growing amount of the waste in the construction industry. Three, further, the conventional approach of casting concrete into a formwork limits geometrical freedom of the architects to build in various geometries. And at the end, the current concrete construction industry is labor intensive and has several issues with the safety. Therefore, additive manufacturing is very attractive approach to solve many of the problems associated with the current concrete industry. It is a smart manufacturing method defined as the layer by layer deposition. For example, with the usage of the 3D additive manufacturing, the total cost of the construction can be decreased between the 35 to 60%. And labor requirements significantly decreased. The amount of the waste materials will be decreased as well. And for the design parameters, which is suitable for 3D additive manufacturing, there are some additional properties that we need to consider during the design of the special material. For example, printing material have to possess some specific properties which is related for 3D additive manufacturing under the fresh and hardened state, as shown in this figure: extrudability, buildability, open time, thixotropy, strength. And printer should be designed by considering the target printing material properties. And in this regard, printing process parameters, for example, nozzle opening, printing path, extrusion rate, print height, or print speed should be adjusted or determined as a suitable for the characteristic of the material. There are several challenges that needs to be solved before developing the materials which is suitable for the 3D printing concrete. And for example, the materials under the fresh state in terms of the 3D additive manufacturing require some properties. One of them is extrudability. The extrudability is defined as the quick and reliable transfer ability of the material with low energy consumption from the storage bin through the printing holes and the nozzle without any blockage and the segregation. In addition, the extruded filaments must be continuous, smooth, and without cracking. These properties can be easily obtained from the conventional material. But as I said to you, we try to develop these properties by using 100% waste material. There is no suitable chemical admixtures available in the market for the geopolymer materials. We need to solve several problems for that reason. Therefore, compared to the conventional materials, this kind of the materials needs so much effort to solve or to develop suitable for 3D additive manufacturing. The other most critical requirement related with the 3D additive manufacturing is buildability. The buildability is defined as the ability of the extruded filaments to possess sufficient yield strength in order to maintain its initial shape under the influence of its own weight and the weight of the consecutive upper layers. This is the second problem that we need to solve. And the other requirements under the fresh state is open time. Look at this example, very simple test. We produce the material in the mixer. So when the mixing is completed, we obtain the sample from these materials, 100% made from the construction demolition waste. When the sample is prepared in the second stage, we remove the molds from the specimen and we put some amount of the weight over the specimen. when we put the weight over the specimen, the shape of the specimen should remain stable. This is the weight around 1 kilogram. And when we complete the test, we put the material inside the mixer again. And when we start the mixing process again, the materials go back to original shape. Look at here, go back to original shape. We call this process is open time. It is defined as the consistent period for buildability or extrudability with acceptable tolerance range. This criterion has a great importance for additive manufacturing because 3D printing is a time-consuming process. As a consequence, all fresh state related parameters should be balanced. Not low viscosity, not high viscosity, not low yield stress, not high yield stress, for optimum printing processes. So here we have an additional lab scale 3D concrete printer. And the first one that I showed you is a simple printer we developed in our laboratory. And in this printer, this video shows one of our initial lab trials by using 100, this is important, 100% construction, demolition, waste-based geopolymer materials without other than actuators. It does not contain any other chemical admixtures. And as seen from this video, an acceptable 3D printing process was obtained. And we are still spending our effort to improve the 3D printing system and development of the methods showed in this video. I also mentioned shortly about the mechanical properties because the methods under the hardened state in terms of the 3D additive manufacturing require some special properties. Sufficient mechanical properties for different direction and the bond strength between the two consecutive layers are necessary in order to ensure printing compatibility of mixtures in the hardened state. And the adequate bond strength between the consecutive layers is a vital parameter to maintain the structural integrity in terms of the additive manufacturing process and the requirement to resist acting shear stress, especially formed by the earthquake effect, for example. And in terms of the mechanical properties of our CDW-based mixtures, it can be first stated that print strategy strongly influenced the mechanical properties of the printed structure. Our nozzle was rectangular geometry, and we cut the printed sample to be cubic sample with the dimension of 3 centimeters. And we loaded the specimens in different scenarios according to the printing direction, and different results were obtained. For example, if we are going to load the samples perpendicular to the printing pad, resulted 32 megapascal. If it is parallel to the printing pad, the compressor strength is going to be 27 megapascal. It's very close, but still we are working on these performances to be equal. If the bonding is going to be perfect between the two layers, these two compressor strength values is going to be close to each other. So as a conclusion, if we summarize the findings that I have mentioned in my presentation, 100% CDW-based geopolymer binder with the sufficient strength even at ambient temperature can be developed. It can be possible. And the ductile engineering geopolymeric composites contributes to, we are expecting infrastructure safety, durability, and the sustainability of the material. And these material exhibits isotropic behavior without additional, this is very important, we can obtain these properties from the conventional material. There are several samples or structures constructed by using the conventional materials by 3D printing application, but this is 100% waste material. Therefore, without any additional chemical admixtures, we can easily design the material which is suitable for 3D additive manufacturing at similar cost to the conventional concrete. Normally, any material, any conventional concrete which is suitable for 3D printing application is very expensive. 3 or 4 times more expensive than the conventional concrete, but our price is similar to the conventional material. CDW-based printable geopolymer composites can be produced from the components available in any region of the world or our country, and it's very easy to print. Therefore, it is important to note that higher performing construction methods, not only in terms of the mechanical durability and workability properties, but also in terms of the sustainability point of view, are necessary for next generation structures. And engineering geopolymer composites, we call like this, with 3D printing capability is leading in this class of the new materials. So thank you very much for all. I think I have already consumed my time, and I will be glad to answer if you have any question.
Thank you, Dr. Shahmaran. It was very interesting topic. Thanks again for your valuable presentation, improved our knowledge. Dear participants, if you have any questions, we can receive.
I think there is one question in the chat. It's asked by the Mahfuz. He asked whether this material can be cast on the Mars. I know some groups, they are concentrating on the development of the buildings out of the world in the space. And the main problem in the space is not related with the 3D system. The main problem in the Mars, for example, is related with the ingredient of the material for the concrete production. For that reason, it's suitable to use the 3D system to construct the building in the Mars or in other places. But the problem is the ingredient or construction. In our case, we use activator and construction demolition waste, and we need to print it. But in the Mars, they need this material. I know some groups, they are concentrated on the subject of the sulfur concrete, because in the Mars, sulfur is available with significant quantity. And when the sulfur is mixed with the water at high temperature, it can be printable. And when it cools to the room temperature, it's going to gain strength. Therefore, this kind of the construction application can be suitable even in the Mars, but the problem is they need to solve the materials problem.
Dr. Yumrutash, raising hand for questions.
Thank you very much, Dr. Shahmaran. I want to ask a new question about the cost of this kind of materials, because the cost is an important parameter to apply this kind of materials. Here, there are some additional costs. I think, if, for example, a transportation cost from demolition area to the factory, maybe to the laboratory, and then back again to the construction area. The cost is important in terms of applying these kind of materials, and maybe also some additional costs such as mixing, such as obtaining grain size, the proper grain size. So what about the cost? Did you think this is effective, or you didn't consider the cost? Just this study focus on the improving about the application.
So in our every step of our research, we keep the cost points in our mind all the time. So first of all, let's start for the conventional material. For the conventional material, for the production of the cement, they obtain the raw material from the nature, and they burn in the rotary kiln, and then they grind. The same process can be applied for the aggregate production. They obtain from the natural source and then crush to the aggregate size. So in our cases, we obtain the construction demolition waste free. It is sourced in all of the lands. And then we just apply crushing and milling. This process has already available in the conventional material. And for the production of the cement, we eliminate the burning process totally because we do not need any burning process. We just crush and milling. This is the one thing. Plus, construction demolition waste is available in all around the Turkey easily. The second thing.
Sure.
The third point is you do not need to bring this material to the laboratory. Just crush and mill the powder and then mix by using the conventional mixer in ready mix truck, for example. So therefore, one, you use all the waste to the valuable material. Two, instead of wasting to the landfill, you use it for the construction process. Three, in normal materials, you waste all of your mountain sources. You do not need to waste all of your mountain or the sources. And the only main cost is coming from the alkaline actuator, but which is at feasible level. When we compare the cost of the conventional material and the cost of the geopolymer system, both of them are comparable to each other. But if we consider in terms of the environmental effect, we have a huge contribution to the environment.
Okay, thanks.
Thank you very much for your question.
Another questions? No. There is no any questions, another questions. Thank you, Dr. Shahmaran, for a valuable speech. Dear participants, I want to say important announcement. Another keynote speaker, Dr. Erdik, will deliver his speech at 1:40 p.m. today. Symposium will continue with the paper presentation. Session 2 will start now. The moderator of this session will be research assistant Yusuf Bahçacı. Raise hands, please raise hand, Yusuf Bahçacı. Click to raise hand.
Yes, I'm here, Dr. Efendi.
Now, you are the host, Mr. Bahçacı. I wish conveniences.